Whoops. Okay. So let's say we wanted to find a tangent, the slope of a tangent at a specific point on the curve of a function. So I'm just going to put it over here. Okay, and we don't know what that point is, so let's say I have an axis here. It doesn't really matter what the axis looks like, but over here, this would be an x value of a, let's call it a, and this would be f of a. Okay, now I'm going to call this point P. And our goal is to find the slope of a tangent line. So we're kind of drawing a line that's touching the curve at that point, and we want to find the slope. Okay, so what we did a couple days ago was we drew another point Q. The difference was that we actually had a specific point. We were just using a hypothetical point, but we had a specific point with numerical coordinates. And we drew another point Q. And we moved Q closer and closer and closer and closer to point P and recalculated the slope. Okay, so we choose point Q. And what I'm going to do is I'm going to say, let's say that this is over here. X. Okay, actually I should have put, and this is going to be x, f of x. That would be the coordinates of those points, right? This point would be a, f of a. Okay, so point Q is going to be x, f of x. And what we did the other day was we calculate the slope of PQ, right? So we found that slope using those two coordinates. And if you remember the slope formula, right? y2 minus y1 over x2 minus x1. So here, our y2 and our y1, or our, let's say our x1, y1 is a f of a. Oh, there should be another bracket there. And our x2, y2 is x f of x. Okay, then the slope of this line segment PQ would be y2 minus y1, so f of x minus f of a. Whoops. Over x2 minus x1. Okay, so we chose that point Q, and we calculated the slope. And then what did we do? Did we just do it once? No, what did we do with the point? Yep. We moved Q closer to the P. Okay, so then move Q, capital Q, closer to P, and repeat. Okay, so what we're doing is we're moving this point closer, or another way of looking at it is we're moving X closer to A. Okay, so how we can actually define the slope of the point, of the tangent line at this point is we can define it as a limit. And I'm going to actually erase this so I don't have to write it out again. You don't have to erase the whole thing. And write this instead as the slope of the tangent line is equal to the limit as x approaches A of this. Because essentially what we're doing is we take this hypothetical point Q, which is like a variable point because we're moving it closer and closer and closer, and this specific point P A f of A, which is fixed. And to get the slope, we move x closer and closer and closer and closer to A. Okay. Now obviously we can't just put an A in for x because A minus A is 0. So we're going to have a problem there, and we're going to see how that works out. And we're going to look at that through an example. This is one way that we can define the slope of a tangent line. Okay, so as an example, find the equation of the tangent line to the curve y equals x squared plus 4x minus 3 at the point 2, 9. Okay, now where does this 9 come from? The 9 comes from the fact that if you plug in a 2 in for x into this function, the y value is 9, right? So if you go y equals 2 squared plus 4 times 2 minus 3, you're going to get 4 plus 12 minus 3, which is 9. Okay, so that's why you have those coordinates 2, 9. Okay, well, to get the equation of a line, we need the slope and either the y-intercept or a point. So we've got a point, that's good. Now we need the slope. So what we're going to do is we're going to use this. Okay, the slope is equal to the limit. In this case, the A value is 2. Right? So our A f of A in this case is 2, 9. Okay, so the slope is the limit as x approaches 2 of f of x. Now in this particular example, f of x is this. Okay. Maybe I'll actually just write the whole thing out first. Be f of x minus f of 2 over x minus 2. Let's write that out first, and then we'll do substitutions. Okay. So now what we want to do is we want to sub in for f of x and sub in for f of 2. Okay? F of x is this. F of 2 is 9. We're going to see what happens. Okay, so m is going to be the limit as x approaches 2 of f of x, which is x squared plus 4x minus 3 minus f of 2, which is 9, over x minus 2. Okay. Now what we can do see what happens up here. So this is going to be x squared plus 4x, and then minus 3 minus 9 is minus 12 over x minus 2. So what can we do with that? Factor it. Yes, we can factor it. And how does that factor? Yeah. Right. It factors into x plus 6 times x minus 2 over x minus 2. And now we have addressed our problem because our denominator cancels out with that factor in the numerator. Okay. Now we can do a substitution because when we plug in 2, we don't have an undefined value. So we're going to get 2 plus 6, which is 8. So m is 8. Okay. Now we're not done yet, though, because we were asked for the equation of the tangent line at that specific point. So to get the equation of the tangent line, right, we have to remember y equals mx plus b. We've got an xy point, which is 2, 9, and m is 8. Okay, so we can just sub those values in and solve for b. So we can sub in a 9 for y equals m is 8 times 2 plus b. And that is, I think, -7. Yeah. B is -7. Okay, so the entire answer at the end of the day to the equation of the tangent line is y equals 8x minus 7 at that specific point. Okay. What's that? Yes. Is that good? Okay. Yes. So A is always going to be a number. A and f of A will always be a specific number. And x and f of x is always, or will always be variables. Okay, now just to make things interesting, there's actually another way that we can, there's another way that we can use limits to define the slope of the tangent line. So we're going to look at that too. And it's pretty similar. Okay, so don't worry. It's not too complicated, but again, let's say we take the same point, PQ, and here's P, and this is also a f of A. Whoops, I forgot the second bracket again. And then instead of having another point x somewhere along the line, this other point, what we'll do is we'll add something to a. So let's say we added a specific amount to a. I'm going to call it h. So if this is 0, let's say, and this is a, and then I've added h, this over here would be a plus h. And this gap would be h. Does that make sense? Okay, so this point is going to be q, and the x coordinate would be a plus h, and then the y coordinate would be f of a plus h. I know this sounds a little crazy, but it is important because this definition of the slope is going to actually help us generalize when we move into the next unit, so that when we're working with a particular function, we maybe don't have to come up with the slope at a given point every single time. Maybe we can come up with like a function to represent the slope of the tangent at any specific point of a particular function. And that's why this definition is important. Okay? Does this make sense to you so far? Are we good so far? Yeah? Okay. So again, slope is equal to y2 minus y1 over x2 minus x1. So if I'm looking at the slope of PQ, right? I'm not going to write a PQ in here because I know eventually it's going to be the tangent line. I don't want to have to erase again. I'm going to leave a gap here. I would have y2 minus y1, which is f of a plus h minus f of a, because this is my y2 and this is my y1. So f of a plus h minus f of a over x2 minus x1, a plus h minus a. Okay. Now, when I set things up this way, and I move Q closer and closer and closer to P, what I'm doing is I'm making the gap between these 2 points along the x-axis smaller and smaller and smaller and smaller. And the gap is h. So I'm getting h going smaller and smaller and smaller and smaller and smaller and smaller. H is approaching 0. Okay, so what I'm doing is I'm zooming in here, and this gap is decreasing, which means h is getting closer to 0. So what I'm looking at is the limit as h approaches 0. Okay, now why is this a problem? Well, if you look at the denominator, okay, a plus h minus a is just h. So if I have an h in the denominator, I can't put a 0 in there. And this is the other way that we define the slope of the tangent line at point A. Okay, so we're going to practice using this one to solve a couple problems. Okay, so find the equation of the tangent line to y equals 2 over x at the point 0.54. Okay, so again, this point is like our a f of a, because if you plug a 0.5 in for x, y equals 2 over 0.5. 2 over 0.5 is 4. Okay, so our a f of a is 'I'll just erase. There we go. I did it again. Must be Friday afternoon. Okay. 0.5. Third time's a charm. 2. Okay, so again, we need slope because we've got a point. If we've got a point and we've got the slope, we can get the equation of a linear function. Okay, so what's that? Oh, it's 4. Ugh, my goodness. There we go. 4th time's a charm. That's a good question. I don't know why it's 2 now. It should be 4. Okay. All right, so the slope is the limit as h approaches 0 of f of a plus h. So our h this time, or a rather this time, is 0.5. Got that right. F of 0.5 plus h minus f of 0.5 over h. Okay, so that's going to be the limit as h approaches 0.
Why is f of a after 5? Should it be, because f of a is 4?
Well, right now we're just looking at f of 0.5, right? So I'm going to put the 4 in the next line. Okay, so the next line is f of 0.5 plus h. We've actually got to plug that into the function, right? So this first piece is going to be 2 over 0.5 plus h minus, f of 0.5, we know what that is. That's 4 over h. Right? So I'm subbing this in for x into the function. I can't evaluate it because I don't know what h is. I'm looking at h as it tends to 0, as it approaches 0. What I'm hoping is that I can do something algebraically here to make the h in the denominator cancel. That's what I'm hoping will happen. Okay, so what would you do with this one? Common denominator, yes. Okay, so the denominator of the 4 is 1, right? What is the common denominator between these two? Yes, 0.5 plus h. Okay, so this is already over 0.5 plus h, but I'll multiply this by 0.5 plus h over 0.5 plus h. Okay, so what I'm going to end up with in the numerator is over 0.5 plus h, 2 minus 4 times 0.5 plus h. Okay. Now what I can do is, well, there's a couple things that I'm going to do. What do you think, where do you think we should go from here? Yeah, so I'm definitely going to distribute this in. What about this denominator? Yeah, I can bring this down. Okay, so let's see what that line's going to look like. The limit as h approaches 0 of, okay, I'm going to write the denominator in first. So h times 0.5 plus h. And then here I'm going to have 2 minus 4 times 0.5 is 2. And negative 4 times h is minus 4h. Okay, so I think this is looking pretty good. Because 2 minus 2 is 0. So in the numerator, all that's left is negative 4h over h times 0.5 plus h. Okay. So I think I've solved the problem. I think we've solved the problem, right? Because now the h's will cancel. I've got a factor of h in the numerator that I can cancel with that problematic factor of h in the denominator. Okay, what can I do now? Sub, yeah, substitute, exactly. Okay, so this is going to be negative 4 over 0.5 plus 0. And that is negative 8, I think. Okay, so now to get the equation, right? Our xy is 0.5, 4, there we go, and the m value is negative 8. Okay, so I can solve for b. And just plug in everything. 4 equals negative 8 times 0.5 plus b. And that should be 4 equals negative 4 plus b. b is 8. Ah! 2 steps ahead of myself. So b is 8. Okay, so the entire equation is going to be y equals negative 8x plus 8. Okay, do we have one more? I think we have one more. Okay. We could do this one both ways. I don't know how much time we have left. Let's do it the second way first, and then when we have time, we'll do it the first way. Okay? So find this, here we're just finding the slope. That's easier, okay, because you don't have to find the equation after. Okay, so at the point 2, negative 2 on the curve, y equals the square root of 2x minus 4. Okay, so, oh, you know what? I just realized something. Yeah, okay. So I haven't given you guys the formula sheet yet for this course because you haven't needed it yet, but I'll give it to you today, okay? One of these two is on the formula sheet. The other one isn't. It's the second one that's on the formula sheet, okay? What's that? For this coming quiz and the first unit test, yeah, I could ask you to use either one. I think I'm going to give them to you, though, if I ask you for them. I don't think I'm going to ask you to memorize them. Yeah. Okay? Yeah. Yeah. Okay. So the first one, well, let's do the second one first. To be honest, the second one is going to be more useful to you. That's why the second one's part of your formula sheet. Okay? So let's do the second one first. Well, we'll see. We'll see how much time we have. We have 20 minutes. We'll see how much time we have when we're done. How about that? Okay. So, and this is our A, F of A. All right. Okay, so M is going to be the limit as h approaches 0. Now, f of x is the square root of 2x minus 4. So when I'm plugging in f of a plus h, actually, I should just put in a 2 here. That would make things a little easier. F of 2 plus h minus f of 2 over h. Okay? I need to plug in, for this first part, a 2 plus h in for x for this function. Okay, so the limit of this first part is the square root of 2 times 2 plus h minus 4 minus f of 2, which is negative 2. Over h. Okay. Let's clean this up a little bit. It's a little messy. There's too many signs. Okay, so m is going to be the limit as h approaches 0. Put in my denominator. This is going to be the square root of 4 plus 2h. That's good. I distributed. So 4 plus 2h. That's okay? Yeah. I actually don't even know if I need to do that. We'll see. And then I've got minus 4, and this is going to become plus 2. So minus 4 plus 2 is 2. Minus 2, sorry. Okay, there we go. All right, what do you think would be useful to do here? Whatever it's called. The conjugate, yes, because I've got a radical plus or minus something. Okay, so I'm going to multiply by the conjugate over the conjugate. And the conjugate of this is the square root of 4 plus 2h plus 2. I should put this in brackets, actually. Okay. Okay, so in the numerator, I'm going to have 4 plus 2h minus 2 times 2, which is 4, over h times that conjugate. Square root of 4 plus 2h plus 2. And I think this is going to work out. Okay, so how does the numerator simplify? 2h, yeah, because the 4 minus 4 is 0. So this is just 2h over h times the square root of 4 plus 2h plus 2. Now the h's cancel, yes. So these cancel. And now I can sub in a 0. So this is now 2 over the square root of 4 plus 2 times 0 plus 2. That is 2 over square root of 4 plus 0 is square root of 4, so 2 plus 2. Two over 4 is 1/2. So the slope is 1/2. Okay, would you guys like to do it the other way? Some of you say yes, some of you say no. Okay, we could do it the other way. If you want to start working on your homework instead, that's fine too. Yes?
Okay, that bottom part there, why? Because wouldn't that just be square root of 6?
No, because it's 2 times 0.
0, right?
Yeah. Okay. All right, so the other way that we can do this is this way. So what was our function again? I can't even remember. It was, I got to go all the way back. Okay, so the function was y equals the square root of 2x minus 4. Okay, I got to write that down. And the point was 2, -2. Okay, so this is still our a f of a. That's still important. Okay, so the other way that we can do this is that m is the limit as x approaches a of f of x minus f of a over x minus a. Okay, so for this scenario, I'd be looking at the limit as x approaches 2 of f of x minus f of 2 over x minus 2, because my x value is 2. Okay, so now we just got to plug some stuff in. So we know what f of x is. of x is the square root of 2x. Was it plus 4 or minus? Oh, no, it's minus 4. Minus f of 2 is negative 2. Minus negative 2 over x minus 2. And I think it's going to work out very similarly in terms of the process. This is square root of 2x, and then minus 4 minus negative 2 is minus 2 over x minus 2. Okay, so where are we going to go from here? Conjugate again, yeah. And that's probably because the original function had a radical in it, right? So when that happens, we tend to have to use the conjugate. So we're going to multiply both by the square root of 2x plus 2 over the square root of 2x plus 2. Okay, and then in the numerator, we're going to get 2x times 2x, or sorry, the square root of 2x times the square root of 2x is 2x. And then 2 times 2 is 4, so minus 4 over x minus 2 times the square root, I made that 2, of 2x plus 2. What can you do with this? Factor it, yeah. So I'm just gonna like cross this out because I don't feel like writing another line. This is 2 times 2x. Or 2 times 2 times x minus 2. There we go. Right? And then the x minus 2's cancel. And you're left with 2 in the numerator and square root of 2x plus 2 in the denominator. And now you can sub in, right? So this is going to become 2 over the square root of 2 times 2 plus 2. And that also works out to be 1/2. Yeah, it does. Well, it does, but there's a problem when we want to. So eventually, and by eventually I mean like in about a week and a half, we're going to want to be even quicker than this. Meaning that, wouldn't it be nice if instead of having to find the slope of a tangent at every single point for every single x value of a particular function, to be able to just have another function that gives us, you know, like an equation where we can just plug in whatever x value we want to get the slope immediately to get that slope. Okay? This version of the slope of the tangent line doesn't get us there, whereas the other version does. And that version, the second one, which we did before, that's called a derivative, and that's our next unit. Okay, so we have to go through this first, so you can have an understanding of where this all comes from. But finding the slopes of tangent lines will become a very, very quick process in a couple weeks from now. Okay.